All right, so this little recording is about how to use the genetic code, which is this thing right here, this chart that I don't think I've, you may have seen it before, but we haven't really used it yet. I want to make sure that I show you how to do that. So again, remember that what we've been learning about is we've been learning about DNA, and we've been learning about protein synthesis last week. The whole point of having DNA and the whole reason why people got all dressed up and the Queen came and everything when Watson, Crick, and Wilkins won that Nobel Prize, because they discovered the structure of DNA was a helix, and wow, that was such a big deal. Well, why was it such a big deal? I mean, what is it about this molecule that is so important that makes it, gets everybody all excited? Okay, so the reason why DNA is so important, even though it's just sitting there in the nucleus of every one of your trillion cells, is because it is the information that directs the making of proteins. Well, why is that so important? Because proteins make up just about everything about you. If you touch your hair, you're touching protein. If you touch your skin, you're touching protein. You look at your eye color, you're looking at the effects of pigments, which are made of protein. The chemical reactions in your body that are happening, they're keeping you alive. That's all enzymes, which are made of protein. Proteins are the working molecules of your body, and what directs them to be made and made correctly is the DNA in your cells. That's the connection, DNA to protein. So let's talk about that. First of all, you already know that if you have a DNA strand that's, let's say, let me see if I can do this right this time without making it. Let's say we're starting with T, 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 and then we go C, G, C, and then we have A at the end. Let's do a simple one. So let's say that that's a DNA strand. The DNA has unzipped, and now we're going to transcribe it. All right, we're going to go through transcription and make an mRNA molecule. And this is going to happen in the nucleus because DNA can't leave the nucleus, right? So along comes that RNA polymerase, and it's going to make a bit of messenger RNA. So remember that when we're transcribing, it's always going to be, every T is going to become an A, right? Every A, though, becomes a what, since it's RNA? A U. Excellent job, guys. Yes, because RNA has U and not T. C's are the same. C's become G's, and G's are going to transcribe to C's. There. So using these, this is basically Chargaff's rules here, right? Chargaff was the one that discovered that. So the T then is going to be A, right? This T here transcribes to another A. This transcribes to another A. What about this C here? Becomes a G. You guys should be doing this in your heads before me. This becomes a C. This becomes a G. What about the A? U. Very good. It's real easy to fall into that T trap there. Be careful, right? And so we have 3 U's at the end. Nice. Okay, so there's my transcript. Now, messenger RNA is going to go out into the cytoplasm. It's going to find a ribosome. And on the ribosome, it's going to go through translation, the second step in protein making. And here's where you use this thing, where you use the genetic chart. So we're going to make an amino acid chain. We're going to make a string of amino acids. So here's what you need to know. You see that the chart does things in groups of 3 over here. So the ribosome puts amino acids onto a chain in groups of 3. So every 3 bases, every 3 messenger RNA bases is translated into a single amino acid down here. So every 3 bases codes for a single amino acid. And the way that you do that, if you look at the chart over here, All right, so if I have AAA, I go over to the chart, I do the first letter first, that would be here. Here's the A, right? My second letter is also an A, so I go all the way down here. Here's my first two letters. And my last letter is also an A, third letter. So my answer for the first amino acid is this, lysine, lice for short. There's my first amino acid, lysine. Okay. My second one, GCG. So now I'm over here. Here's my first letter, G, and then C. So this column right here, C, and G. Here it is. There's the codon. And I'm going to have alanine be my second amino acid. Alanine. ALA for short. Okay. My last one is UUU. Which one's that? Somebody tell me.
If you're confused,
PHE. Yes, you got it, Maddie. There it is. UUU gives you PHE, which is phenylalanine. But all you have to do is write PHE and you've got it. Right. So there's your amino acids, and that, I mean, there really aren't any proteins that are only made of 3 amino acids. It's going to be hundreds of them, but there's a small chain of amino acids which becomes a protein eventually, right? If you keep going with this, you'll have lots of amino acids in a string, and that becomes a protein. Okay, so let's just do a few more. What if, hold on a minute. Let's see. What if instead of, let me give you another codon. What if you had your messenger RNA codon was a, what if it was an AUG? What does that give you? MET, very good, methionine. And the reason why it's outlined in red is because methionine is very often the very first amino acid in every protein. It's sort of called the start amino acid. Sometimes it's called the start. Generally signals the start of the amino acid chain. Okay. What if you had UGA instead? You find UGA? Because anytime you start something, there must be a way to stop it. So there you go. UGA is one of the codons that codes for the protein to stop getting made, right? You got to have a signal to stop it if you had a signal to start it. Okay. All right, so that's how you use the genetic code, guys. That's why DNA is important, because it allows the body to make all of these proteins in your body that make you who you are. So I'm going to stop this recording.